Today lecture 27. This is, we are kind of in between modules 9 and 10. So, the goal of this lecture is to wrap up the discussion on mixers and move on to oscillators. Now, while we are transitioning from one module to another, you will find out how these two connect with each other. All right. So, in the last class, we developed the super heterodyne architecture, right, and the reason why we developed that was to accommodate for one of the important non-idealities that arise out of this mixing operation, that is a DC offset, right. So, any kind of local oscillator leakage into the RF port of the mixer will cause a DC offset, and this DC offset has drastic, it really creates a drastic performance variation as far as direct down conversion receivers are concerned, right. So, because this particular local oscillator leakage is variable, it varies over process, from process to process, varies over temperature, it varies with parasitics, right. As a result, this leakage is variable. Now, if the leakage is variable, the DC offset is also variable, and it is something that we cannot tolerate, because under direct down conversion you are actually translating the signal all the way to DC, and if you have a DC offset on top of that, then that is going to cause problems. So, that is why we went for super heterodyne architecture, and why we call it super heterodyne is because you can have multiple heterodyne stages. You can have one IF stage, you can have a second IF stage, a third IF stage, and so on and so forth. Sophisticated radios have, I have seen up to 3 IF stages in sophisticated, extremely sophisticated radios could have 3 intermediate frequencies. So, 3 heterodyne stages, it is all called super heterodyne, right. The reason why we have these multiple intermediate frequencies and not just one is because of the image frequency, because every time you do a heterodyne stage, there exists an image frequency which can also translate to a frequency which is the IF frequency. So, if there is a blocker at the image frequency, then the blocker will go right on top of the desired frequency and will cause interference, right. So, this is the reason why we need to put an image filter before we do the mixing operation. Now, the image filter has certain limitations, it can't be of extremely high quality factor, right. We can afford to make a filter of a quality factor of 10, right, which means that there is a certain restriction on where the image frequency can be in relation to the RF frequency. I am sorry, not image frequency, yes, where the image frequency can be in relation to the desired frequency. Now, this means that there is a restriction on what the IF, that is the intermediate frequency, can be with respect to the RF, and because of this we went for multiple heterodyne stages, that is the super heterodyne, right. Now, with this background, the next problem that we have not really a problem, more like a suggestion. Think about this. Let us talk about the transmit path. Okay. So, in the transmit path, this particular signal, it is not the RF here, this is the message, and over here we have got the local oscillator. And this is the RF output. All right. So, this is the scenario in the transmit path. Now, this message that we are talking about, suppose it is voice, just crude assumption, it is no longer voice is no longer directly sent like that, but anyway let us say it is voice, right. If it is voice, then the spectrum of the message is something like this. So, x axis is the frequency axis, and if you look at how the signal is, the signal will look something like this, right. This is typical for a voice signal. It is going to be restricted to 20 kilohertz, because human speech or even music does not contain frequencies beyond 20 kilohertz, and there is also a lower cutoff. Lower cutoff is around 20 hertz, 40 hertz, something like that. You normally do not hear frequencies below that. Whales can communicate at even lower frequencies, human beings can't, and bats can communicate at frequencies higher than 20 kilohertz, human beings can't. So, that is ultrasonic and subsonic. Right. Ultrasonic is the bats can communicate beyond 20 kilohertz, whales can communicate below 20 hertz or so, human beings can't. Human beings speak within 20 hertz and 20 kilohertz, something like that. All right. So, this is the characteristics of voice or music, audio. Now, when you translate this to RF, let us say that the local oscillator, it is A cosine omega t, right. It has two impulses at plus minus f naught, right. This is the Fourier transform of the local oscillator. Okay. And when you do a mixing operation of this particular local oscillator with this particular message, what you wish to get or what you are going to get you are going to convolve the spectrum of the local oscillator with the spectrum of the message, and when you do the convolution operation, this is what you are going to get. Okay. You are going to get modulation of the message to the RF frequency, to the local oscillator frequency. So, around f naught you will get two side lobes. Now, the suggestion that came is that this is wasteful. So, why this is wasteful is because this is f naught minus 20 kilohertz and the other one is f naught plus 20 kilohertz, which means that the net bandwidth that I am using is 40 kilohertz, right. So, that is why I am saying that it is wasteful. My information contains stuff from 0 to 20 kilohertz, but I am using up a band which is 40 kilohertz wide, double. it is wasteful. In any case, one side lobe is the mirror image of the other one. So, there is no new information in the second side lobe, right. There is nothing new in the other side lobe. That is why it is wasteful, that is why I am saying it is no good. So, the suggestion was that let us get rid of one of the two and let us transmit only one of the two side lobes. So, we do not want to transmit both of these. Spectrum is a valuable resource, costs a lot of money, and we are just wasting half of our money over here, and it is very wasteful, no good. Both the lobes contain the same amount of information, the very same thing. So, let us get rid of one. Now, it is easy to say let us get rid of one, it is very difficult to actually get rid of one of the two. How do you propose to get rid of the two, one of the two? So, let us think about it in a different way. Let us say that my message is cosine omega m t, omega message t, and let us say that my local oscillator is cosine omega 0 t. Okay. When I multiply the two, I get cos omega m t times cos omega 0 t, right, and I presume you are abreast with your trigonometry, and you can split a product of two cosines into a sum of two cosines. Cos A times cos B is half of cosine A plus B plus cosine A minus B. Am I right? I think I am right. So, this is what happened. This is actually what happened when you did the convolution. This is just talking about it from a trigonometry point of view as opposed to doing the Fourier transform and doing convolution. Now, is there a way to get rid of one of these two components? I would like to keep this, let us say I would like to keep this, but I do not want to keep this one. There should be a way. So, what do I need to generate? I need to generate cosine omega m plus omega naught t minus cosine omega m minus omega naught t. If I can generate this new term and I sum the two things, then I have got rid of one. And how do you generate this new term? How do you generate this new thing? Cos A minus cos B is twice, you have forgotten your trigonometry, right? Okay, I will help you. What is this? What is sin A times sin B? Sin A times sin B, remember, all you have to remember is this. This is ridiculous. I am teaching trigonometry in an RF electronics class, but what can be done? So, if you just remember these two things, then you do not need to remember hundreds of different formulae. These two are sufficient. right. You are interested in this particular term sin A times sin B. So, sin A times sin B is clearly going to be half of cos A minus B plus I am sorry, half of cos A minus B minus cos A plus B. Which is really this. Right. And now, if I do a subtraction or an addition of some sort, then I get rid of the term that I do not want and I get to keep the term that I want. If you do an addition, then you do the other way, right. You can also do an addition. If you do the addition, then this one will cancel out, the other one will stay. That is what will happen if you do an addition of these two. Right. So, this is how you would generate a single sideband modulation system, right. One of these paths is called the in phase, the other path is called the quadrature phase. So, this is called the cosine is called the in phase, the sine is called the quadrature phase. So, this you do in the transmit side, and on the receive side you do something very, very similar, right, and you can reconstruct the message. Is there any problem over here? There is a problem. The problem is, there are two problems. One is, if my message is cosine omega m, how do I generate the sine part of it? That is problem number 1. And problem number 2 is, if my local oscillator is generating cosine omega naught t, then how do I generate sine omega naught t? Right. So, these are problems, two different problems. Well, problem number 1 is not very difficult to solve. You have to understand that these messages are no longer audio signals. We are not talking about audio signals anymore. These are some form of digital signal. It is actually coming from a D to A converter, right. So, there is going to be a processor which is going to create this message, and if the processor can create the cosine part of the message, it can equally create the sine part of the message. So, it is being generated by some sort of digital signal processor. So, as far as the message is concerned, if cosine can be generated, the sine can also be generated, there is no problem. What about the oscillator? The oscillator has to be designed in a way that cosine and sine are generated hand in hand. Okay? You make your oscillator such that it generates both an in phase and quadrature phase at the same time. So, in phase is 0 degrees, quadrature phase is 90 degrees shifted from in phase, 90 degree offset from the in phase. So, it is possible to design an oscillator which will generate in phase and quadrature phase at the same time, right. So, this is something important when we study oscillators, which we shall start today hopefully. We have to make sure that we understand how to generate in phase and quadrature phase together at the same time. Okay? It is important. do not let me get away without explaining these ideas. All right. Now, as far as the receiver is concerned, let us now think about the receiver. The receiver is receiving something from the antenna. This is what I am receiving from the antenna, and then there is an LNA, low noise amplifier, etc., etc. All right. And now, I want to figure out cosine omega m t, that is my message, cosine omega m t and sine omega m t as well, maybe, right, that is my message. How do you propose to do this? I have to do exactly the same thing. So, if I multiply by cosine omega naught t, then what am I going to get? Cosine times cosine, cosine times cosine looks like the sum of two different cosines, the sum of cosine a plus b plus, right. Cosine of minus theta is the same as cosine of theta. Okay. What happens if I multiply it with a sine? Cosine times sine what is cosine times sine? Cosine times sine is really looking like let us say this particular term, right. So, it looks like the difference of two sines. Sine of minus theta is equal to minus of sine theta. All right. And then if you low pass filter these, I can get rid of the high frequency component. There is a component at somewhere near twice omega naught. All I need to do is put a low pass filter and I will get rid of that particular component. So, this component can be gotten rid of using a low pass filter. So can this one, and what you are going to be left with are cosine omega mt and sine omega mt, right. This is straightforward. Only problem here is to once again generate cosine omega naught t and sine omega naught t at the same time. So, once again when we design our oscillators, we need to learn how to make quadrature oscillators. So, this particular thing is called the I path and this is called the Q path, in phase and quadrature phase. There are two paths over here, right. So, this is the basic idea of in phase and quadrature phase. Now, of course, no one really thinks the way I have described it to you. This is for your basic understanding. Normally, people deal with complex signals. They treat the signal like a complex signal, and it is like the sine path, the quadrature path is what you are doing to the imaginary part of the signal, and the real part of the signal is the in phase path, and so on and so forth. But this is a more realistic treatment, and I hope that if you keep this kind of a treatment in mind, then when sooner or later you come across a treatment which uses complex numbers for in phase and quadrature phase, it will be clear to you, right. Okay. So, this is one particular suggestion. The suggestion was, why are we wasting bandwidth? We should be utilizing just about enough bandwidth as there is information. The problem, of course, the problem is that this cosine and sine generation is never perfect. You have to be perfect. They have to be exactly 90 degrees away from each other, cosine and sine. If they are not, then you are going to get an image. So, as far as your transmit path is concerned, in your transmit path, the desired output is over here, impulse at omega 0 minus omega m, right. If you do a bad job as far as the quadrature path is concerned, then you are going to get an image of this at omega naught plus omega m. Of course, the image will be smaller than the desired signal, because you have done something over there, but because you have done a bad job, it will not be much lower than the signal. It needs to be 0. It will not be 0 because you have done a bad job. And why have you done a bad job? Because you have done a bad job as far as generating sine omega naught t is concerned. You have done a bad job over here. So, maybe you have done a bad job at all of these places, and because you have done a bad job, there is going to be so many dB of rejection between the in phase path and the quadrature phase path. Okay. The next thing is that both of these two mixers that you have made two mixers, they have to be identical mixers. They have to have the same gain, they have to have the same conversion loss, right, the same characteristics. Otherwise, the amplitudes of these two signals over here are going to be different, and if the amplitudes are different, then they do not exactly cancel each other, which means once again that you have resulted in a bad job as far as the image cancellation goes, and you are going to get some image next to the desired signal, and you are going to transmit this also, right. So, the wireless standard that you are following will tell you how much this image can be, how large it can be, how large it can possibly be for your device to be sold in the market, right. So, you have to do a good job over there. The same scenario is as far as the receiver is concerned. As far as the receiver is concerned, if there is mismatch, or rather if there is some alignment issue between cosine and sine omega naught t, then you are going to receive something in addition to what you wanted to receive in the first place. So, if there is a blocker where the image signal is, then that blocker is going to come on top of your signal and it is going to harm you, right. And as far as this is concerned, there is no hard and fast rule about how large, how good your quadrature phase has to be with respect to the in band phase, yes, the in phase, whether it has to be perfectly 90 degrees or 89 degrees is good enough. No one is going to tell you. What they are going to tell you is the blocker size is this much, now do what you want, right. The size of the blocker next to your signal, desired signal, is so big. Now, will your receiver work? If it works, it works. If it does not, it will not sell in the market. All right. The next thing, this particular oscillator that we are talking about, the all important oscillator, how good can an oscillator be? So, the question is, if I say I am the base station, you are the cell phone. Base station, that is me, I am telling you to go to a frequency of 1.254 gigahertz. Now you are the handset, you go to 1.254 gigahertz according to my wishes, because I am going to send you some signal at 1.254 gigahertz. However, your definition of a second is different from my definition of a second, because we are not on the same chip, right. The transmitter, the base station is somewhere and the receiver, the handset is somewhere else far away from the base station. So, the handset has no idea of what the base station means when the base station is saying 1.254 gigahertz, right. The definition of second as far as the handset is concerned could be a little different from the definition of second for the base station, which means that the definition of what 1.254 gigahertz means as far as the base station is concerned could be a little different from what the handset thinks, which means that instead of going to 1.254 gigahertz, maybe the handset goes to 1.2545 gigahertz. Is it good? It is no good, because you have tuned to a wrong frequency, and if you have tuned to a wrong frequency, then you are not getting all of the signal, your entire receiver is gone astray. So, when I talk about 1 second, you need to know what exactly that second is. We need to have a common definition as far as 1 second is concerned. What is the definition of a second? You must have read in studied this in your class 12 or something like that, class 10. There is a definition of a kilogram, a definition of a second, definition of a meter, right. Some standards are kept in some museum, and these are, that is the definition of a kilo, right. Some object that is placed in a museum somewhere in London, I do not know. You remember that? And then the second, as far as the second was concerned, it was so many oscillations of some krypton or cesium atom. Remember that? Cesium atom, right. So, there we go. That is the definition of a second. You pick your brain, I do not remember the exact definition. There is a number of oscillations of a cesium atom or a krypton atom, keeps changing from time to time. So, what does that mean? So, there is the cesium atom or krypton atom and it is vibrating, and when it vibrates so many times 1 second has elapsed. Rather, the krypton atom is vibrating at so many hertz, a frequency of so many hertz, so many cycles per second, right. So, this is your atomic clock. You have heard of atomic clocks? So, the atomic clock is the most precise definition of time, and so many vibrations of the atomic clock gives you a second. Rather, the atomic clock is vibrating at so many hertz. So, this is defining hertz for you, right. So, if you look at the Fourier spectrum of the output of an atomic clock, the Fourier spectrum of an atomic clock will look like two perfect impulses. So, let us say the vibration it is at some cos omega naught t, I do not know the exact number, but this is how the spectrum of the output of an atomic clock is going to look like. Any other clock, not atomic, any other clock, the output is not going to look like that. Guess what? The output of any other clock, which is not an atomic clock, is going to look like this. All right. And all of that garbage, so you hope that it will be two impulses, it is never going to be two impulses, only the atomic clock will have two impulses at plus and minus omega naught, everything else will have some junk around the impulse. So, this junk is called phase noise. Okay. That is called phase noise. So, the oscillator, whatever it is, it tries to oscillate at a perfect frequency. It cannot oscillate at a perfect frequency. There is some noise around that frequency, that is called phase noise, right. Now, what are good oscillators available in the market? The cheapest form of a good oscillator is a quartz crystal. It is available widely in the market. If you are wearing a wristwatch, most probably it is a quartz wristwatch. Just check. If it is running on a battery, it is likely it is a quartz crystal. There is a quartz crystal inside, and quartz crystals have extremely good phase noise characteristics. They are still not perfect, they are extremely good, that is all I am saying, right. Very low phase noise, and to quantify the phase noise, I am not really going to try to quantify the phase noise, I am going to quantify the jitter in the clock. So, the variation in the timing is about 10 parts per million. If you buy a good quartz crystal in the market, it is not very expensive, 50 rupees, 100 rupees, you will get a good quartz crystal, and the jitter is of the order of 10 parts per million. What that means is that the quartz crystal, when you buy it, something will be written on it. It will be written maybe 30.0001 megahertz. Okay. So, that means that that particular crystal oscillates perfectly at 30.001 megahertz, each period of oscillation is 1 by 30.001 million seconds with some jitter, and the jitter in that period is 10 parts per million or something like that. You will get it from the data sheet for that particular quartz crystal. It is of the order of 10 parts per million usually, right. So, coming back to the question, the definition of second of the base station has to be the same as the definition of second for the handset. Now, the handset is not going to be carrying an atomic clock, right. Cheaply available is a quartz crystal. All handsets will have a quartz crystal, and that will give the handset a rough approximation as to what the definition of a second is. And then there is going to be some handshaking between the base station and the handset. The base station is probably going to send a pilot tone somewhere, which will be known to the handset to be at a certain frequency, and the handset will define its second based on that particular pilot tone. So, this is typically what is done. How does the base station define its second? What is the definition of a second? Two base stations, they will have different definitions of seconds, and if they have different definitions of seconds, communication in between them is going to go haywire, right. So, the base station, what it does is it talks to a GPS satellite, right, and on board a GPS satellite there are atomic clocks, and if a base station is able to talk to 4 GPS satellites at the same time, that is the idea. If I can talk to 4 GPS satellites at the same time, then the x, y, z coordinates and the time coordinate can be fixed, right. So, we are really going out of bounds of this particular course over here. This discussion is going away, but that is basically the idea. The base station talks to 4 GPS satellites, figures out what the time is. All the base stations talk to 4 satellites. These satellites on board carry atomic clocks. So, the base station definition of second is synchronized with the definition of second of the GPS satellites, which are defined by atomic clocks. Now, each handset synchronizes its definition of a second with a pilot tone that is coming from a base station, and as a result the second is defined everywhere. This is basically the scheme of things. Now, we go back to the oscillator. So, this particular oscillator has phase noise. Okay. So, presumably you are going to build some local oscillator, and this local oscillator unfortunately will have phase noise, all right. Now, think about it in a different fashion. Let us say that at the antenna I am receiving my desired signal, and right next to the desired signal I am receiving a blocker. All right. Let us say that the desired signal is at 1 gigahertz and the blocker is at 1 gigahertz plus 100 kilohertz, let us say 200 kilohertz, and let us say that the blocker is 60 dB larger than the desired signal. All right, under worst case situations. So, what does that mean as far as my oscillator is concerned? How good does the phase noise of my local oscillator have to be? Let us take a look at that. So, this is the situation. I have got a desired signal, I have got a blocker which is 60 dB above the desired signal, 200 kilohertz away from the desired frequency, right. What does the spectrum of my local oscillator need to be so that I do not corrupt my signal? So, it is easy to understand that 200 kilohertz away from the desired signal, from the desired LO. Let us say this is my LO, 200 kilohertz away if I have got something, then that something is going to modulate with my blocker. So, that something is going to multiply with my blocker signal, right, and the resulting product is going to come on top of my desired signal at the output. So, that means that this separation has to be 60 dB, more than 60 dB. Okay. So, this is the way we define phase noise. So, phase noise is defined in this fashion: 60 dB with respect to the carrier at an offset of 200 kilohertz, right. So, the definition of, so how you talk about phase noise is like this: I need 60 dB with respect to the carrier, my phase noise has to be 60 dB less than the carrier at an offset of 200 kilohertz from the center frequency. All right. So, this is the way I define the phase noise of an oscillator, and this is where the requirement comes from. It is a very basic requirement. There is a blocker next to the signal, I cannot corrupt the signal. Okay. So, this is minus 60 dBc if I want 0 dB of signal to noise ratio, signal to blocker ratio, right. If you want more dBs, then the phase noise specification will go up. All right. So, let us now move to oscillators. Okay. So, important as far as the oscillator is concerned, an important specification is the phase noise of the oscillator, and you kind of understand that phase noise is related to jitter. It is like there is an uncertainty in what the period of the vibration is exactly, right, that is where it is coming from. What are the other important parameters? What are the other important thoughts that we have? We need quadrature, so I need to be able to generate sine and cosine at the same time. Anything else? Not at the moment. Okay. Now, what are popular methods? What is the most basic oscillator that you can think of? Think of your high school, class 12. Alright. So, this is the most basic oscillator. There is an inductor and a capacitor, and if you do the analysis, you can show that energy will be stored in this oscillator, and it will keep getting transferred from the capacitor to the inductor. So, on the capacitor it will be stored as a voltage, as charge, and in the inductor it will be stored as magnetic flux, a current, right, and it will keep shuttling back and forth between the inductor and the capacitor. And if you observe the voltage across these 2 points, you will see that the voltage is a sinusoid, some sort of cosine. Okay. At what frequency? At the resonant frequency. The resonant frequency is 1 by 2 pi square root of L C. Alright. So, this is the most basic oscillator. Unfortunately, this kind of an oscillator is not practical. Why? Why is this kind of an oscillator not practical? Because you can never make these perfect components. The wire will have resistance, the capacitance will have some leakage, the inductor will have some series resistance. In fact, the inductor resistance is what is going to hurt you the most. Okay. So, as a result, this is not possible to make. You will always end up with this, and as soon as you end up with some series resistance, oscillations in this circuit are never going to be sustained. If at all they start up, they are going to get damped and they are going to go down to 0 soon, very soon. Right. So, this is basically the problem. You can model L in series with R as L in shunt with R. It is possible to model a series L and R to a shunt L and some other R. You know how to do this, right. And even then the oscillations are not going to be sustained. Okay. So, what can you do over here? So, one thought is that let me invent a new component which is a negative R, and a negative R in shunt with a positive R is as if you have got an infinitely large resistance in shunt. An infinitely large resistance in shunt is as if you have got nothing in shunt, and in that case the system is going to start oscillating and the oscillations will be sustained, right. So, this is the thought that maybe I can invent a certain component which has an effective impedance of minus R, and I am going to put it in shunt with this tank. This is called a tank. Okay. The R is not intentional. The R that is drawn inside the tank is not something that is intentionally there. It is something that has arisen out of imperfect components, right. You never you are never going to put a real resistance over there, fine. It is called a tank, I do not know for what reason. It could be that because energy is stored in this particular tank circuit, energy is stored and it keeps getting transferred from the inductor to capacitor back and forth. Okay. So, that is probably why it is called a tank, I am not sure. Anyway, so this is the basic idea, it is called a tank circuit. Right. So, this is one thought process. Another thought process which you might be familiar with are using ring oscillators. So, you could think of your digital circuits, you could think of an inverter, and let us say I put 3 inverters in feedback, make a ring. If each inverter has a delay of d, then this particular circuit is going to oscillate somehow, it is going to oscillate at a frequency of 1 by 6 d. Right. So, this is a second line of thought. A third line of thought is as follows, that you remember your amplifier design, etc., etc., and you remember poles and zeros and so on. What if I place some poles on the j omega axis? If I am able to place poles on the j omega axis, then my system is going to oscillate. So, this is a third line of thought. This will generate perfect cosine. If I manage to place the poles on the right half plane, if I manage to place poles on the right half plane somewhat like this, then the system will have a response which is a rising exponential times some cosine. Now, of course, a system is never going to keep growing in terms of voltage. That probably means that the output is going to get saturated at the power supply voltages, which probably means that I will end up with a square wave. Okay. So, this is going to give me a square wave. Remember, we like square waves. So, this is a third line of thought. All right. Now, we are going to try to stop here, and in the next class we are going to see how all of these 3 lines of thoughts are actually one and the same, right. They all are actually exactly the same thing. You are placing, eventually you are placing poles on the j omega axis or outside the j omega axis on the right half plane, etc. Okay. So, this is the basic idea, and we are going to see this in the next class when we carry our discussions further. Okay. Thank you for your attention.